Okay. So basically, this sheet, we need to solve an inequality like this, right? Okay. You can refer to this page. And last time we haven't done example 3 and 4. So let's have a look at example 3 and 4 first, okay? Okay, example 3, solve the inequality here. Okay, as you can see here, this is a product of several binomials, right? So usually we call this polynomial function. And if you move everything to the left, the right should be a 0. It's either a greater than or less than 0, right? So if you can transform that into this form, then you can consider the function on the left. And let's say you need to consider the function y equals okay, basically the left is a polynomial function. So this is a polynomial function. And it's already in a factored form. A factored form means it's a product of several binomials, okay? If it's in a factored form, it's easier because it's easy to calculate the zeros, right? Okay, so because this is a polynomial function, first of all, consider its degree. Now, how do you calculate its degree? Degree is just how is the possible order of the independent variable x, right? So you can just count how many x's are there. So you have 2 here, right? X squared, two x's, 2 and 2 and 3. So 2 and 2 and 3 is 7. Then let's consider the leading coefficient. Okay, leading coefficient, there is also a shortcut to find its leading coefficient. It's just the product of all leading coefficient in these binomials, right? Okay, for the first factor, leading coefficient is -2. So because there is a square, so leading coefficient -2 squared times 1 squared times, this is -1, right? So -1 is the leading coefficient of this binomial. Do not forget there is a cube here. So basically this is, sometimes you don't even have to calculate the value, right? As long as you can decide whether it's greater than 0, less than 0, that'll be fine, because this is you want to solve the inequality. So this is a positive, negative. That must be a negative number. Okay, next we find its zeros and orders. Or we call it zero with orders, zeros with orders. What is there? Orders. Okay, first of all, if this expression is 0, it's easily to see that zeros are 1/2, -1 and 7, right? So first of all, we have 0 as 1/2. Orders means how many times does this binomial repeat? So it repeated twice. So that means the order for x equals 1/2 is 2. We have order 2. And next one is x equals -1. Again, it's repeated twice. So that means the order is 2 as well. Next, we have x equals 7. So this binomial appears 3 times. So the order of x equals 7 is 3. Okay, then based on this information, we can sketch its graph. Degree is a odd number, and the leading coefficient is positive. Also, we have all the zeros. Then we can sketch its graph. Okay, if degree is an odd number, it will have a end behavior like this or this, right? Either this or this shape depends on the leading coefficient. If the leading coefficient is a negative number, then it must have a shape like this, right? For the end behavior. Oh, sorry, I missed. Let's erase this. Okay, degree 7, which is odd number, leading coefficient is negative. So that means end behavior will look like this. And then we mark all the zeros. So first of all, the -1, then 1/2, then 7. Okay, then we need to sketch the behavior in the middle. So first of all, as x increases from -infinity, first will come to -1, right? So whether it goes this way or this way depends on the order at this 0, right? Okay, because the order is 2 at x equals -1. So according to the sheet here, at any 0 that has a even order, the sign of this function does not change, right? So it will bounce back to this direction because before -1, it is greater than 0. Because that's not change sign here. So after -1, it should be also a positive, right? Okay, so then it will go this way and cross the next 0 here. And then let's check the order at this 0. Order is 2 at x equals 1/2. That means the sign does not change either. So it will bounce back again. Then it will cross the next 0 at 7. At x equals 7, the order is 3. Order 3 is a odd number.
You can continue.
Okay. At any 0 that the order is an odd number, the sign should change, right? So before this 0, it's positive. So after this 0, it will become a negative number. Then basically it will have a sketch like this. Okay, and do not forget our task. Is to find any interval that can make this function be less than or equal to 0, right? So let's check which interval can make this function less than or equal to 0. First of all, x can be -1. Then x can also be 1/2, right? So this point is okay, this point is okay, and from this point on to the negative to the positive infinity, that also makes this function equal to or less than 0, right? That means or x can also be greater than or equal to 7, right? So this is our solution. Understand? So this sheet is a key to solve, to sketch the graph of this function, and then you can use a sketch to solve an inequality like this. Understand? Okay. All right, then let's have a look at the next one. Okay. All right, this time again, if we move everything to the left, then the right side is a 0. So we have already converted the inequality in the general form. And left side is a product of several binomials, right? Product of several binomials is a polynomial function. So we can consider the function on the left. Usually you need to explicitly write that consider the function y equals the expression on the left. Okay, such that your reader can understand what are you talking about here. Okay, if you consider the function like this, then this is a polynomial function, right? I'm not going to write here again. First of all, the polynomial function degree is, okay, let's count how many x's are there. So 2x's, 3x's, 1, so degree is 6, right? Next, let's consider its leading coefficient. A leading coefficient is, shortcut to calculate leading coefficient is a product of all leading coefficients in this binomials. So first of all, -2 squared times -1 cubed, right? Next one is just -1. And this is a positive number, negative number, negative number. So the product, these three numbers, will be a positive number, right? Okay, it's positive. Okay, 6 is a even number. Then you can refer to that sheet. If it's an even number, leading coefficient is positive, then it will go actually this way, right? And behavior will be like this. Then you need to consider the behavior in the middle. That depends on the zeros and their orders. And let's consider the zeros and their orders. Okay, so luckily, the function has already been in a factored form. Factored form is easier to find all the zeros, right? If you let y be 0, you can just simply find either this is 0 or this is 0 or this one is 0, right? So that means the zeros are, first of all, x can be 1/2 with order 2, right? Order 2. The next x can be 1 with order 3. Then x can also be 7 with order 1. Well, it's usually by default, if we don't write anything here, by default, the order is 1. So when its order is 1, don't have to write anything here, because by default, the order is 1. If it's not 1, please write it explicitly here and here. Okay, then next. The end behavior, as we said, if you have an even number degree, it will go like this or this, right? But because the leading coefficient is positive, so the end behavior will be like this. Because as x approaches to negative infinity, y will approaches to positive infinity, and x approaches positive infinity, y also approaches positive infinity. Then let's consider the behavior in the middle. First, we can mark all the zeros, 1/2, then 1, then 7, right? Again, not necessary to scale as long as you keep the elements in their correct relative positions. Okay, so this function will go this way as x increases from negative infinity. First, the function curve will arrive the first 0. At first 0, we need to determine whether we should go this way. That means the sign does not change, or this way. That means the sign does change, right? That depends on the order at this 0. Okay, the order is 2 at 1/2. So that means when it's an even order, the sign does not change. So before the 0, the function is positive. After it, it will also be positive. So it will go this way, right? Then it must cross the next 0. So it will go back to the next 0. Then let's check if this 0, will it change sign? The order is 3 at x being 1. So that means it will change sign at this 0, right? Because the order is odd. And also it states on that sheet. Okay, next, it must cross the next 0. Then before you go any further, we need to determine at this 0, it will go this way or this way. So the order at x being 7 is 1, which is also a odd number. So that means it must change sign at this 0. That means it will go this way, and then it will connect to its end behavior like this. It will go this way all the way to positive infinity, right? So basically, this function here has a sketch as the figure shown here, right? Then as using this sketch, we can find any interval that can make this function, this is our function, right? That can make this function less than or equal to 0. Okay, so let's find all the intervals that can make this function less than or equal to 0. First of all, this point will do, this point will do, this point will do, and less than or equal to 0, this interval will also do, right? Therefore, we can know that the solution is actually x can be 1/2, or x can also be within 1 and 7 inclusive, right? This is our final solution. Any questions?
No.
Oh, okay, again, you can see here, this sheet is a key to solve this problem. Okay, then let's have a look at our assignment. Assignment 4, question 1, which is actually similar to the problem we have discussed, right? So first of all, we can consider the function y equals x plus 3, y minus x, x minus 5, right? Again, this is a polynomial function. Luckily, it's also in a factored form, so it's very easy to find the zeros. Okay, so let's find first the degree. 1, 2, 3, just 3 x's. It's multiplication of 3 x's is x cubed, right? So the degree is just 3. Then let's consider the leading coefficient. Okay, from now on, I'll use LC to denote leading coefficient, okay? Leading coefficient is just a product of all the leading coefficient of the factors. So 1 by -1 by 1 is less than 0, right? Next, let's consider all the zeros and their orders. Okay, first, x can be -3 with order 1. Then x can be 1 with order 1 as well. Then x can be 5 with order 1, right? Okay, so based on this information, we know that first of all, degree is even number. Even number leading coefficient is negative, so that means it will have end behavior like this, right? Then we consider the behavior in the middle. First of all, -3 is a 0, 1 is a 0, 5 is another 0. Okay, so this function will go all the way to the first 0. Then, because all of them has order 1, so they change sign at each of the zeros. So change sign, back to the next 0, change sign, then back to the next 0, change sign. Then we'll go like this, right? Okay, and our task is to find any interval that can make this function greater than or equal to 0, right? So greater than or equal, this means this interval will do. Also, this interval will also do, right? Therefore, the solution is x is either less than or equal to -3, or x can also be in this interval between 1 and 5 inclusive. Okay, so the first question is simpler because everything here is in a factored form. Okay, next one is a little complex because apparently this factor is not in a factored form, right? Okay, so what's so special about this expression here? So let's have a look at what can we do about it. Okay, first of all, let's consider, okay, if not all the expressions are in a factored form, first of all, we can consider this expression here, whether this expression is always greater than 0 or always less than 0. If it's also greater than 0, that means the later part must be also greater than 0, right? So first of all, we can convert it to the squared binomial. So let's try to do that. Okay. So note here, x squared plus x plus 4. This is actually 2 times x times 1 over 2, right? So if you want to convert it to a squared binomial, probably we can try using x plus 1 over 2 squared, right? And if you expand this, you will get x squared plus 2ab means x plus b squared, which is 1 over 4, right? But there is no 1 over 4, so we need to subtract it. So this expression here must be equal to this one. And copy the rest of the expression here. So basically, x squared plus x plus 4 can be rewritten as this form, which is x plus 1/2 squared plus 15 over 4, right? So is this expression always greater than 0 or less than 0? Can we decide that? Okay, how about the first part? If x can be an arbitrary number, first part is something squared, right? Something squared must be non-negative, right? So the first part of this expression is greater than or equal to 0, right? And then plus a negative number. Then how about this whole expression? Is it always be greater than 0? It's always a positive number, right? Okay, so that means this part is always positive. No matter what x is, it's always positive, right? Okay, so let's mark it as asterisk. The original expression must be equivalent to, okay, if the first part is always positive, the product of the first part and the second part here is a positive number, right? Does that mean we know the sign of the second part? If the first part is always positive, the product of these two parts are positive. That means it must be equivalent to the second part must always be positive, right? It cannot be negative number, right? Otherwise, positive times a negative must be less than 0. So that's not the solution, right? Okay, so by our analysis here, actually you can just simplify by eliminating this first part, right? You don't have to consider that because this part is always greater than 0. Or you can think in another way. If this part is also positive, we can divide both sides of the inequality by a positive number, right? That does not change the solution and does not change the direction of the inequality symbol, right? So first of all, if you can see any part of the left side is not factored, then first of all, you can try whether we can simplify this. Okay, so as you can see here, the original expression can just be simplified to this one. We can just solve this inequality. Actually, there are only 2 factors. And actually, this is a quadratic equation, right? For a quadratic equation, actually, you don't have to use this method because we have known that for a quadratic equation, it will have a shape like this or this, right? Okay. First of all, what's the direction of opening? Can you tell that? Direction of opening. This way or this way? Opening up, right? Because leading coefficient is positive, so it's opened up. Then how many zeros are there? 2, right? One of them is -3 and the other one is 2, right? And we know it's opening up, so it must have a sketch like this. So this is just its sketch. Then we find any interval that is greater than 0, right? And it's not very difficult to see that this interval can make this function greater than 0, and this interval can also make this function be greater than 0. Therefore, the solution is either x is less than -3 or x is greater than 2, right? Okay. And what is the takeaway here? Takeaway here is if you see any part of the left side is not factored, first of all, try to think whether this part is always greater than 0 or always less than 0. If it's always greater than 0 or less than 0, then you can try to eliminate it by dividing both sides with this expression, right? To simplify the original inequality to a much simpler one. Okay.
Okay.
All right. In question 3 again, as you can see here, probably we can. This part is not totally factored, right? So whether you can either try to factor it or examine it. It is whether it is always greater than 0 or less than 0, right? Okay. So can you see that? Whether we can factor this. First of all, we can try using the cross multiplication. X can be factored to x by x. Note here, 15 can be factored to 3 by 5, right? Okay, 3 by 5 is 15. Then by cross multiplication, we'll get 5x plus 3x, which is 8x, which is a term in the middle, right? So actually, the later part can be factored as well. Then, first of all, let's convert that one into a factored form. So the original expression is just equivalent to 2x minus 3 times x plus 3, then times x plus 5, right? Then this form is what we are familiar with, right? Everything is totally factored. So that means we can consider the function on the left. Let's mark it with y equals 2x minus 3, x plus 3, then x plus 5. Okay, then we consider this function. First of all, the degree. So what is the degree here? 1 to 3 is just 3, right? Okay, how about the leading coefficient? 2 by 1 by 1, which is greater than 0, right? Then let's consider all the zeros and their orders. Okay, first of all, x can be 3 over 2, right? With order 1. Okay, x can be 3 over 2 with order 1. You don't have to write it here. X can also be -3, right? With order 1 as well. Then x can be -5 with order 1. Okay, then we can analyze its function. First of all, degree 3, leading coefficient greater than 0. Okay, according to this table, degree is odd, leading coefficient is positive, then it will have a shape like this, right? Okay, shape like this means this one. Then there are 3 zeros. 3 zeros, first one, -5. Next one, -3. The next one, 3/2. Then let's consider the behavior in the middle. That depends on the order at each of the zeros, right? First of all, this function will go all the way to the first zero. Then, because each of the zeros have order 1, so that means this function will change direction, will change sign at each of the zeros, right? So first of all, it will change from negative to positive. Then cross the next zero, change from positive to negative. Then crosses the next zero, changes sign from negative to positive, and connect to its end behavior on the right side. Okay, so basically this function have a shape like this. Then remember that our task is to find any interval that makes this function less than or equal to 0. Okay, so less than or equal to 0 means this is a possible interval, and there is another possible interval here, right? Therefore, the solution is x is either less than or equal to -5, or x is greater than or equal to -3, and less than or equal to 3/2, right? This is our final solution. And what is the takeaway here? Takeaway is if you see a expression like this, you can try to factor it first, right? In order to convert it to a problem that you are familiar with. All right, next one. Okay, next one. Okay, this expression. Okay, first expression is in a factored form already, right? And next one is not in a factored form. Probably we can factor this as well, right? Okay, so if we consider this function, y equals r minus 3 squared, then 4r squared minus 25. First of all, this is just 2r squared minus 5 squared, right? And using the formula, we know this can be factored to 2r plus 5, then 2r minus 5, right? Because it's simply a squared minus b squared. A squared minus b squared is a plus b times a minus b. Okay, in this way, the second part of this expression is factored to 2r plus 5 times 2r minus 5. Okay, again, this expression is, we have seen a lot of expression like this, right? We are familiar with this because everything in this expression is in a factored form, right? That means we can't factor either further, right? Okay, then for this function here, the degree is, so how many r's are there? 1, 2, 3, 4. So degree is 4, right? Which is even. And next, leading coefficient is, okay, 1 squared times a 2 times a 2. So that means leading coefficient is greater than 0, right? Okay, next, let's find all the zeros and their orders. First of all, R can be 3 with order 2, right? Order 2. The next R can be -5/2 with order 1. Then R can also be 5/2 with order 1, right? Okay, so let's check the table. Degree is even, is whether this one and this one. Leading coefficient is positive, so that means we'll go this way, right? And behavior is like this. Then we consider behavior in the middle. So first 0 is -5/2. Next one is 5/2. Next one is 3, right? Okay. All right, so as x increases from -infinity, this function will cross the first 0, and then let's check, does it change sign here? Okay, at r equals -5/2, the order is 1, so it does change sign from positive to negative. So it will cross this point. Then go to the next point, also with order 1. Order 1 is a odd number, so it will change sign here, right? From positive to negative from negative to positive, right? Then it will go all the way to the next 0 at r equals 3 because order is 2, which is an even number, so that means it does not change sign. So before this 0 is positive, after this 0 it will also be positive. Then that means bounces back, then connect to its end behavior, right? So basically we'll have a shape like this. Then our task is to find an interval that makes this function be greater than 0, right? And it's easy to see that this interval can make this function greater than 0. This interval will do, and this interval will also do, except at these zeros. Because at these zeros, simply makes this function equal 0, not greater than, right? Therefore, the solution is either r is less than -5/2, or r is between 5/2 and 3 exclusive, or r can also be greater than 3, right? Any questions? No? Okay, then let's have a look at the next one. Okay, next one, everything is on the left already, and the right side is a 0. So let's consider the function on the left, right? First of all, you can just copy that. And note here, if it's not simplified, first of all, our task is to try to simplify this function, right? Okay. Or before we do this step, if the original inequality is not simplified, we can just even simplify the original inequality. Okay, so first of all, apparently there is a common factor 2 in the first part, right? So we can put 2 in front, then what's left there is x plus 2 then squared, right? So how about the second part? Seems that second part is a quadratic equation, right? And first, probably you can try using cross multiplication. It's not very difficult. So -3x squared can be factored to, how about x by -3x? Then because we have a 2 as the constant, right? So 2 can be factored 2 by 1, right? Then in this way, by cross multiplication, remember that we need to do some trial and error test. So this is -6x plus x, which is -5x, which is term in the middle, right? So that means all factoring here is correct. Okay, so the second part can be factored to x plus 2. Then -3x plus 1, right? And if you're not sure, I strongly suggest you to verify result because this is just your first step. You need to make sure the very first step is correct. Okay, so always remember to verify if your factoring here is correct by multiplying it back. So if you expand everything, you will get -3x squared, -6x plus x plus 2. So -3x squared, -5x plus 2. Okay, that means all factoring is correct. All right, this one should be less than 0. Then this is actually 4x plus 2 squared, then x plus 2, then -3x1 plus 1 less than 0, right? Okay, so what's next? We can divide both sides using a 2, right? Using a 4. Okay, so equivalent to, can divide both sides using a 4, right? 4 is a positive number, so that does not change the inequality direction. So that means x plus 2 cubed times negative 3x plus 1 should be less than 0, right? Right? And as you can see here, the original expression is actually simplified to this one, right? And we are already familiar with a inequality that has this form, right? Okay, then we can consider the function on the left. Let's consider this function now. Okay, the degree is 1, 2, 3, 4, right? Because there is a multiplication of 4 x's. So the highest order of the expression is 4. That means degree is 4, which is even number. How about the leading coefficient? Leading coefficient, first one is just 1 cubed, right? Times second one, negative 3, which is the less than 0, right? Okay, then let's find its zeros and their orders. Okay, first of all, if we let this expression be 0, because all of the terms in all of these expression is in a factored form, we can easily see that the first 0 is just x equals negative 2, right? And note here the order of x being negative 2 is 3, right? You need to write it explicitly if it's not 1. Next, x can also be 1/3, right? With order 1. So order 1, we don't have to write it because by default it's 1. And next, and behavior. Degree is even and leading coefficient is negative. So which one do you use? Degree is even here, right? And leading coefficient is negative. So you need to use this one, right? So first of all, the end behavior will look like this. Then there are 2 zeros. One of them is negative 2 here. Next one is 1/3. Then the function will go all the way from negative infinity to the first 0 here. And at the first 0, we need to determine whether it will change sign, right? Does it change sign here?
Yes.
Order 3, yes, order 3 is a odd number, so it will change sign from negative to positive. Then it will cross the next 0, right? And because the order is 1, which is odd number, so it will also change sign here, right? Okay, then it will go all the way here is end behavior like this. We will go like this, right? Okay, then based on the sketch of the graph, we can decide the interval that makes this function less than 0, right? So less than 0 is this interval and the interval on the right side. Therefore, the solution are x is either less than negative 2 or x is greater than 1/3. Okay, next one. Next question is a little complex. Okay, let's read it first. Find all values of k such that the solution of the inequality here consists of only one single interval, possibly infinite on the number line. Okay, also I gave you a hint here because we don't know the value of k yet, right? So you need to discuss under different values for k. What does the graph of this function look like? So basically, you can see, let's consider the function. actually you can try to solve this inequality, right? You can just solve this inequality as what we did in the previous questions. So first of all, let's consider the function on the left side, which is y equals the product of these three binomials. Then, what's the degree here? Because in order to solve the inequality, first, usually we'll discuss the corresponding function and find its degree and leading coefficient, right? Because this is a polynomial function. So what's the degree here? 3. And what is the leading coefficient?
1.
1, 1, 1. It's 1, right? Which is greater than 0, right? And actually 3, you can write it here as a reminder that 3 is actually a odd number. Okay, so how about the zeros? Zeros can be 2, right? And also x can be 5, order 1, right? And x can also be k with order 1, right? Okay, so let's consider. So what's the next step? Next step, we try to sketch the graph, right? But because we don't know where is k, let's say it's easier to find the relative position of 2 and 5, right? So k can be either here, or here, or here, or here, or here, right? So how many cases are there?
Infinite.
1, 2, 3, 4, 5. There are 5 different cases, right? You understand?
Mm-hmm.
So you need to discuss the different 5 cases. Okay, let me restate, because this is our 2, this is our 5. Either k is here or here at the 2 exactly, or here between 2 and 5, or here at 5 exactly, or here if k is greater than 5. That's 5 different cases, right? So in these 5 different cases, you need to discuss them one by one to see what will happen. So first of all, let's see if k is less than 2, what will happen? Okay, if k is less than 2, if this is 2, this is 5, k must be here, right? Okay, first of all, what's end behavior? And behavior does not change because degree is always 3. Leading coefficient is always greater than 0, right? If degree is a odd number, leading coefficient is positive, so it will go this way, right? Okay, that means the function will go all the way from negative infinity all the way to the first 0. Then because at each of the zeros, the order is 1, right? So it will change sign at each of the zeros. So change sign at first 0, change sign at second 0, change sign at third 0. So basically, this is a sketch of the function. If k is less than 0, less than 2. Okay. How about the second case? Second case, k can be a little larger, right? And this time k can be exactly 2, right?
Mm-hmm.
Okay, if k is exactly 2, that means, can we draw a number axis? Okay, if k is exactly 2, that means there are only 2 zeros, right? X being 2 and x being 2. That repeated twice, right? So that means, okay, first of all, we have a 2 and 5 here. Again, the end behavior does not change. End behavior always go like this and this, right? And do not forget, this time, the 0 of x being 2 has order 2, right? Because you have here and here. It happened twice. So first of all, the function will be bounced back because it will change. It does not change sign at any zero that is an even number order, right? It will bounce this back and then go to the next zero with order one, so it will change sign. Then it will go all the way like this, right? So this is a sketch of the function 1k is exactly 2. And there is a third case. If k is between 2 and 5, what will happen? If k is between 2 and 5, then we know this is 2, this is 5, and this must be k, right? And again, the end behavior always look like this. And first of all, the function will go this way, and again, at each of the zeros, the order is just 1. So the function changes the sign at each of the zeros, right? So it will go like this. Change the sign at each of the zeros. Okay. So how about the fourth case? Fourth case is if k is exactly 5, right? And can you try to sketch 1k is exactly 5? If it's exactly 5, there will be only 2 zeros. And remember that the end behavior always look like this, right? So it will go all the way to the first zero. Then which way should I go? This way or this way? Up or down?
Mm, um,
What's the order of 2?
order,
1, right?
yeah.
Happens once. So order 1. 1 is even number, changes sign. So it will go this way, right? Then all the way here. Then at this point, at this zero, because this zero has order 2. So it does not change sign. So before this zero, it is positive. So after it, also be positive. So that means bounces back all the way like this. Okay, so there are 4 cases. How about the 5th case? Okay, I can wait for a little while.
Sorry.
Okay, last case is k can also be greater than 5, right? So if k is greater than 5, then the relative positions between among these 3 zeros are 2, then 5, then k, right? Because this time k is a number that is greater than 5. Okay, and behavior still look like this. Then it will go this way to crossing the first zero, and did change the sign because this all of zeros have order 1, right? Then cross the next zero, then cross the next zero. Then we'll have a shape like this. So we can solve this inequality in each of the cases, right? Depending on the values of k. So in the first one, remember that our task is to find any interval that makes this function greater than or equal to 0, right? So in the first case, what is the solution? Solution must be here or here, right?
Okay,
Okay, how about the second?
it's just 5.
From here to here, right?
Yeah.
And remember that this point will also do this point here. And third case is from here to here. Then from 5 to positive infinity. Then in the next case, this must be from 2 to 5, and from 5 inclusive to positive infinity, right? And next one is this interval, then this interval. Okay, and it's not over yet. The question is, under which cases the solution consists of only one single interval? So can you tell? In which case the solution only consists of only one single interval. So how many intervals are here in first case?
2.
Third case, also 2, right? Fourth case, fifth case.
2.
How about second case?
2.
2. Only the fourth case will do, right? Because in the fourth case, therefore we can say 1k is 5. The solution is, what is the solution? It's just from 2 all the way to positive infinity, right? The solution is x greater than or equal to 2. So only in the fourth case, as you can see here, that means 1k equals 5. The solution is a single interval, right?
Mm-hmm.
Okay, so this is how we can analyze this inequality like this. You can just follow the similar method we have discussed previously. Try to solve this inequality. The difference is that this time we don't know the value of k. That means you can't decide the relative positions between these 3 points. If you can't decide that, you can separate this problem by actually discussing different values of k, right? That's that simple. Okay. All right. Any questions?
No.
No. All right. So probably it's better to practice problems again. I give you another assignment here. The questions are very similar to this one. Okay.
Okay, thank you.
So if you have built up the confidence, we can move on. Okay. All right. And I also upload my notes to